Hi guys, I hope you guys are doing great. Welcome to week number 6 of operating system course. I hope you have gone through all the content we studied up till now in last 5 weeks. If you have any questions, you are free to ask any questions. I can see a lot of students approaching me about different things. It's always a good idea to interact with you guys, although it's through emails or through virtual offices. But what to do now? This is the situation. So please do not hesitate to contact me in case of any difficulty you are having, whether it's related to any topic, anything in general you don't understand, anything you want to comment on. It's always a good idea to hear from students. Anything related to your assignments, I have seen a lot of students came to me regarding assignments. I'm going to discuss something about the assignment in a while before we actually dive into our today's lecture. So please do get back to me about anything regarding the course. Maybe I don't mind hearing a feedback from you guys, how we are doing in this course, how I am doing as an instructor in this course, so that I can further improve myself. It's always a good idea to hear from your students how things are going, because I won't say again it's a very easy course, but I won't say it's a very difficult course as well. So if something is bothering you, maybe the pace we are going at a very rapid pace, although we are not. I'm trying to split all the concepts in such a way that we understand one of the concepts carefully. First of all, we understand everything about that concept, and only then we move to the next concept. That's why if you try to compare some of the concepts we have discussed, and you try and see them in the book, you might see there is a different organization in the book, and we have a little bit change in the organization when we are going through slides. And that's the only reason why I believe that you need to understand some of the concepts before you actually dive into the other concepts or some advanced concepts. So anything you think we can further improve in this course, please let me know. We are halfway around the course, and it's always a good idea to hear from you students, because it will help me in further enhancing this course, further making you guys understand this course. I'm trying to give you as many exercises as possible from my end, but as I said in the beginning of the course, and I keep on saying every lecture, that the exercises I am giving you are not the only exercise you should go through. I mean, I give you maybe one or two exercises, and then I give you one practice exercise. Sometimes I solve that practice exercise for you as well. So you end up getting nothing to practice, right? So it's always a good idea to go to internet. Maybe as I told you in your textbook, there are a lot of exercises that you can practice. So there are so many exercises over there as well. And internet is full of exercises if you want to further practice these concepts. So please do that. The programs we are running, the programs I'm running for you as exercises, you can obviously change them here and there. Try to see how different outputs are generated when you change some things within the code. So try to do some practice. This is the only way I think you're gonna learn about not only the concepts, but actually the practical side of it. So if you think this blend is helping you, then excellent. If you think there is something missing, then you can either approach me or maybe try doing some more practice exercises, so that you actually understand the concepts and the application of those concepts. So this is for this. Second thing is regarding the assignments. I have received almost all the assignments. Now many of the students have solved the assignment, and I think they didn't have any problem. There are more than few students, they had some questions, they didn't have any problem as such, which is good to see. At least I can see that you are diving deep into the concept, and this is exactly why I gave you an assignment on threads section. We could have done an assignment on processes, but threads are even more deeper than processes. So that's why I wanted to give you an assignment on that, so that you can actually do more yourself as well. And I can see a lot of students are learning different concepts which were embedded inside actually that assignment. I mean, it looks pretty straightforward when you see it at the first time, considering we have actually done a very similar exercise on that concept as well. But when you start doing it, you get to see that how a lot of things you start learning. For example, for a lot of students, threads performed really well as compared to single thread for a program where there was no thread. So multi-threaded environment was performing really well for some students as compared to single threaded environment, where, or maybe when there was no thread. Actually there is always one thread. So but for other students, single threaded environment was performing far better than the multi-threaded environment. So those students were actually confused what is going on. It's absolutely normal, as I actually had discussion with a lot of students, but I thought I should explain it over here as well, so that students who got their assignments with multi-threaded environment doing well than single-threaded environment, at least they should know that sometimes there might be cases when single-threaded environments might perform well in might perform well as compared to multi-threaded environment, because your operating system is doing a lot of things at one time, right? Now there can be several reasons when this can happen, when a single-threaded environment might perform better than multi-threaded environment. The reason can be you are not using multi-cores. Even if you are using multiple cores, your operating system is doing so many things at one time. Maybe it has a antivirus running at the background, it has network drivers, couple of network drivers running at the background, you have browsers, you have other applications running, you have some default services installed into your Linux distribution. So many things have been running at the same time, and those processes actually have threads within them. So cores were not available to you when you were running your program. So at that particular instant, when you ran your single threaded program, it ran faster because other threads were actually killed by the operating system for some of the services which were not required that time. But when you started running your multi-threaded environment, your system was actually doing a lot of other things, so that your multi-threaded environment actually became an overhead. Creating threads, multiple threads for your operating system became an overhead for your operating system. So your multi-threaded environment did less efficient job than your single threaded environment. So it's absolutely fine if this is happening. You don't have to worry, you are not doing maybe anything wrong. I've already seen some of the codes from some of the students asking for what they are doing. They were doing absolutely fine, even then single thread environment was doing well for them, and which is absolutely normal, as I said to you. And these are some of the many reasons why single thread environment can do better than multi-threaded environment. So that's one exercise which can actually make you guys understand how threads can perform in complex situations. And we were doing very complex computation, 1 billion, and then adding it to the previous. I mean, it's not easy for operating system to do this job, for a processor to do this job. So we were doing a complex stuff over there, and then we were actually calculating that even numbers. So we were taking a mod as well and then adding those even numbers as well. So it was a complex computation as far as running this on your personal computers with single cores or two cores. Some people might be using 3 cores as well. So it's absolutely fine if some people are having this confusion that maybe their assignment was not done properly and they were so frustrated they ended up just submitting it as it is. It's absolutely fine if your single threaded environment was doing better than your multi-thread environment. Don't worry about that, and I will definitely keep that into consideration, because not everybody's environment is similar to anybody else. So I'm not expecting that your environment is exactly similar to what my environment is. So I don't expect that, I don't assume that. Alright, so don't worry about that. Hopefully that clears up a lot of confusion which other students were having. So if you have further questions, we can further discuss that, but what I really want you guys to do is better to look up on Google as well to find out some other reasons. I've given you some major reasons that can actually help you understand the comparison between multi and single threaded environment, but you can further go on Google to learn more about it, and it will help you get better idea of how threads work. So I hope this is clear for you guys, and you can see there is another assignment number 2 coming up this week. Don't worry, we are not going to do any assignment now this week. We're going to move this assignment to week number 7. So I know this is the middle of your semester, and everybody, all the faculty members are assigning you tasks here and there, and I don't want to be a burden on you guys. I don't want to give you have just done with your assignment number 1, and I don't want to give you another assignment. So I don't want to do that, right? So we can move it further. We can delay it for 1 more week at least, and we'll see what type of assignment. I don't want to give you another challenging assignment of programming. So as I said maybe in the beginning as well, that there are 3 assignments, and we are going to have a mix of programming assignments and some essay type assignments. So hopefully I'll try to give you assignment number 2 as an essay assignment or a report assignment, so you don't have to deal with the code as such. So we'll see what we can do with assignment number 2, but that is not going to be this week. Assignment number 2 will be in week number 7, somewhere here. So our course flow would change. I'm not going to change over here, but I'm going to tell you verbally, I'm telling you verbally that we are going to move this assignment number 2 to week number 7. All right. So this is for this. I think we should move to lecture number 6 now. Our lecture number 6 is again regarding processing, and this time it's about CPU scheduling. You will see a lot of algorithms today as well, and I hope these algorithms are not as much coding algorithms as the previous ones. We are going to I'm going to run you through some of the algorithms which I'm going to program later in the exercise part of the lecture, but in the theoretical part we are not going to hopefully see a lot of code, not at all code, I guess, if I'm not wrong. And then in the code I will show you how to do it. So hopefully in the theoretical part we'll see mostly theory and mostly some algorithms, how they perform, what is the theory behind it. So let's get started. So our topic today is CPU scheduling. CPU scheduling, before going into CPU scheduling, we know that at one time operating system is dealing with several processes, right? And those processes have to acquire your processor to execute or to do some computations. We know that, right? And we have heard about our CPU and IO burst cycles. So if a process is has acquired a CPU and doing some processing on that, then it's called a CPU bound process. If it has an IO, for example, it's printing something, it's doing that printing a lot more than what it is using CPU for, then it's called an IO bound process. So over here, if we talk about CPU scheduling, the main aim of operating system is to make sure that CPU is not idle at all. So CPU has to be utilized at its maximum at most of the time. So if CPU is done with one process, it's the responsibility of operating system or one component of an operating system to provide the other processor to the CPU. So processors should never sit idle. And how to make sure that processors are not idle, because today we don't have a single processor, we have multiple processors. How to do that? We schedule our processes, we schedule our CPU, we schedule our processors to different processes, and make sure that none of our processor is idle or doing nothing, right? So this is the main job. And how to do that, how to schedule that, because there are different processes, as we have discussed in previous lectures as well. There are some processes that might have higher priority than the other processes. How to schedule them, we'll talk about them today as well. And there are some other algorithms as well. First come first serve is also there, so we'll talk about that. Then there is round robin as well, we'll talk about that as well. So this is what we're gonna do today. So basically if you see this diagram over here, so something is done by CPU, which is maybe loading a file or reading from a file. So this is actually a CPU burst is done, then it's waiting for maybe a printer or something. It's an IO burst, then it's a CPU burst. So basically it's actually combination of both CPU burst and IO burst. We have seen that, right? And when it comes to CPUs, how to schedule CPU tasks is the main agenda of this topic, of this lecture today, and this is what we're going to talk today. So when CPU scheduling actually happens, so there are normally 4 possibilities when a CPU scheduler is initiated, and then our processors or CPU is scheduled to do some tasks. All right, so first of them would be, we know that there are 5 stages for a process. There is a new process, new stage, then there is a ready state, then there is a running state, then there is a waiting state, and then finally there is a termination stage or terminate stage. So scheduling of a CPU works in normally 4 of these stages. So first of all, if a process was running and it is looking for an IO device, for example, it wants to print something, it will not then stay running, it will go to waiting stage, right? because if a processor is using a CPU and then it is looking for a printer, and at the same time it keeps on running waiting for the printer, then none of the other processes will be able to use that processor, right? So it's not a good idea to keep that process in a running state. So if a process is looking for an IO device or something not related to CPU, then it should go to the waiting stage. It should go to the waiting stage, right? So when something like this happens, scheduling happens, because as soon as one process is moved from running to waiting stage, which new process should come to the running stage now? So scheduling is required over here. So this is where CPU schedules the next process to be run, right? Next one is when a process switches from running to ready state. Similarly, if a process was running and for example some high priority process comes over there and it requires a CPU, then the current running process will move to the ready stage, which means that it's not looking for an IO device, it's still ready to run, but because of some reason some other process came that has higher priority. So this process was moved to the ready state and the new process moved to the running state, right? So CPU scheduler will be working over here, which process will come over here that has higher priority, how to check the priority of that process, which algorithm it's taking. So at that stage also CPU scheduler will work. Then the next one is when a process switches from waiting to the ready state. So for example, our process which was here, which went to get a printer, it's done with printer, now it moves back to the ready stage ready state. It went back to the ready state. Now ready state might already have 4 or 5 processes over here. Now this new process, should it go to the end of that ready queue, or should it go in the middle, or should it go at the front of this ready task? So when next time the processor is free, this process can actually go and run. So where should from waiting stage it will go to the ready state? Should it go at the end of the ready queue? Should it go to the front of the ready queue? So that the process can actually go and run using the CPU. So this is where a CPU scheduler works as well. How to schedule this coming new process from waiting stage to the ready stage. This is where a CPU scheduler also works. And last one is, if a process is running, then it terminates, what is the next process that is going to run, right? So this is another process, this is another stage where a CPU scheduler will run. So these are 4 or 5 stages where actually CPU scheduler is gonna work. It's gonna come into work. It's gonna make sure that processor is not waiting just because there was nothing in the queue, or just because 2 processes were fighting with each other that I'm gonna go first. So this is the responsibility of operating system to handle all these things, and how to handle these things is using a CPU scheduler. Okay, so then we have a dispatcher also. So there is a CPU scheduler that is going to schedule, and there is a dispatcher also. What dispatcher does is, some people call it a module, some people call it another component of an operating system. It's up to you. We're going to call it a dispatcher, right? So what dispatcher does is, it gives control of CPU to a process. All right, so basically over here, if you go back, CPU has scheduled that process 1 is going to go to running stage before process 2. Okay, so we have decided that. Fine, so it means that process 1 is going to take CPU next time whenever the CPU is free. So when this scheduling has been done, next step is for the dispatcher component to take process 1 and give CPU to it. All right, it's not going to schedule anything, it's not going to do anything, it's just going to, based on this schedule, it's going to assign CPU to that process, right? And it involves several things. For example, context switching will happen, if you remember. So one of the process will go away from here, go and do something else, or maybe it has completed, so context switching is going to happen, right? User switching will happen because these are user processes. Maybe there can be kernel processes also, so there can be user processes also, so there might be a need of switching to user processes also, so this can also happen. Then if this process was running, so for example, if process 1 was running, if process 1 was using the CPU and process 2 came that time, and process 2 has higher priority than process 1, which has low priority, so operating system will take the CPU from process 1 and give it to process 2. So for example, it has 10 number of statements in its code, C code or Java code, and it has executed only 5 out of those 6. But then CPU process 2 came, and CPU has to be given to process 2 to complete its execution. So operating system came, snatched CPU from process 1 and gave it to process 2, right? So what about the next 5 instructions? So these are, if you remember, we talked about process control block, and we told our operating system, our process actually, that okay, you have executed 5 of them, rest of them will be in process control block of this process. So next time when CPU is given to this process by operating system knows where to start this. So next time operating system goes back to this process 1, it will not start from instruction number 0 or instruction number 1. It will start from instruction number 6, because 5 of those instructions have already been executed. So dispatcher will take control of that. It will read from there and assign the CPU according to that. And then one important thing to note over here is dispatch latency. Latency means delay. So when there is a shift between different processes, there actually is some delay in processing, because for example, process 1 is having a CPU, and operating system wants to give process 2 the CPU. So the time taken by operating system to snatch CPU from process A and give it to process 2 will have some delay, right? During this time, when the process 1 was during the time when CPU was taken away from process 1 and given to process 2, CPU was not doing anything, although this is for only nanoseconds or milliseconds, very small amount of time, but there was some delay, because the time between which the CPU was taken from P1 and given to CPU, maybe 5 milliseconds or 6 nanoseconds or whatever, CPU was not doing anything. Although this time is very small, but still it takes some time, and this time is called a dispatch latency. All right. So these are few things you should know about a dispatcher, and we have talked about CPU scheduler as well. Now let's talk about some criteria of scheduling. How to schedule? I mean, how does operating system know that we have to schedule this CPU, this process first or this process last? How does it schedule that? What is the criteria behind that? Now before we actually dive into the criteria or the algorithm, let's talk about what are the main factors that operating system sees, or a scheduling algorithm or scheduler sees before it actually schedules the processes. So first thing is CPU utilization. We know this, and this is very important, that operating system has to make sure that CPU is utilized to its maximum. It should always be busy. It should not happen that a process is waiting for CPU and CPU is idle, right? It should never happen. So CPU should be at its maximum utilization if possible. It should never be idle. It should always be busy. This is the first thing that scheduling algorithm is going to see. Then throughput, number of processes that complete their execution per time. So it should be done that all the processes should be executed in such a way that maximum throughput is achieved. So for example, in 1 hour 60 processes or 50 processes should be executed. So maximum number of processes should be executed in a given amount of time. So this is called a throughput. So maximum number of processes should be executed in a given amount of time. Then there is a turnaround time. Turnaround time is basically the amount of time to execute a particular process, right? And we're going to talk about this when we write a code. So turnaround time is actually the amount of time that is required to execute a specific process, right? Then waiting time, how much time the process was waiting in the ready queue, right? How much time it took for him to go to the CPU. It was waiting for some time, so that is the wait time. And response time is actually the combination of amount of time it takes from when the request was submitted until the first time the response was produced. All right. So for example, at certain time, operating system was asked by this process that I need a CPU, right? Just to give you an example, for example, at 10 a.m. Of the system time, a process P1 asked for CPU to the operating system, but since CPU was busy, let's assume there was a single core, and operating system was obviously operating system is taking care of all the scheduling. So process 1 came at maybe 10 a.m. and it asked for CPU, and since there is only a single CPU, operating system was managing this CPU, and this was taken by process 2, process 3. So all the processes were there, and they were in the ready queue, or they were in the queue to get CPU. But operating system, process P1 got this CPU at maybe 10:15, right? At 10:15. So this was there was a wait time for the process over here as well, and then it was executed maybe at 10:18, right? So this is all the response time. This is all the response time. So it requested at 10, it got CPU at 15, but it executed at 10:18. So, and you will see that how does it work, because it has a lot to do about time sharing environment. When we'll go through different algorithms, you'll get to know that what this response time actually means. So these are few things that operating system is going to see when it is scheduling different processes. Let's see the algorithm now. How does operating system make sure that these are taken care of well, right? So first thing is the CPU utilization has to be maximum. So CPU utilization has to be maximum at all time if possible. So operating system will make sure that CPU utilization is always maximum. So CPU is always busy. Next thing is going to see is maximum throughput, which means that operating system will make sure that maximum number of processes are executed at a certain amount of time, right? So it will make sure that these two are maximum, right? Then turnaround time. Turnaround time, if you remember, the turnaround time is actually the time to execute that process. So operating system will make sure that less amount of time is taken to execute that process, right? So it should not be given to some other processes if possible. Make sure that this process takes less turnaround time to complete its execution, and there should be minimum wait time as well, right? And there should be minimum response time as well. So if these three are minimum and these two are maximum, it means that operating system is doing an excellent job scheduling all the processes. And please remember that there is not only one process, there can be thousands of processes running at a single time, and then within those 1,000 processes there might be different threads as well, right? So if operating system is doing these things well, it means that operating system scheduler is doing really well, right? So operating system scheduler has to do all these things to make sure that all processes get equal chance of getting the CPU. All right. Now let's talk about these algorithms. So these 4-5 things each and every algorithm has to make sure, right? So because these are scheduling algorithms, so scheduling algorithms have to make sure that these 4-5 things are done exactly like this. So there should be maximum CPU through utilization and throughput, then there should be turnaround time, less waiting time, and less response time, right? So all of the algorithms should make sure that they do something like this. So let's talk about what type of algorithms are there and how they can solve this problem, right? First thing is, and the simplest one is first come first serve. So any process that comes first in the queue, it will run first. So obviously if process 1 came first in the queue and there is no other process, it will run first. Process 2 came second, it will run second. And it will be non-preemptive. We discussed preemption and non-preemption. Preemption means if a process is running and some high priority process comes, then processor will be given to that high priority process, right? Which means that the process 1 or CPU has been preempted. It has been given to somebody else. But in first come first serve algorithm, normally we use a non-preemptive approach, which means that if process 1 is there and there are process 2 and 3 in the queue, process 1 will complete its execution. Even if high priority process comes, it will not be preempted. Process 1 will complete its execution and only then it will be given to another processes. And this is what is written over here. So they should complete their execution. And next process given, I have a diagram over here. So we have this queue. So process 1 was at the front or head of this queue, and CPU will execute process 1 first, then next will process 2, then process 3, then process 4. So all of them, they complete their execution, and only then the processor will be given to the next one in the queue. All right, this is how first come first serve works. But there is a problem. There is a disadvantage of this approach, and the approach is maybe this process will take 10 minutes to complete its execution. Then these processes will have to wait. This, for example, process 1 takes 10 minutes, this takes 20 minutes, this takes 30 minutes, which means that process 4 will have to wait for 1 hour for its execution, which is not at all a good idea. It will keep on waiting. Maybe it only wants to execute for 2 seconds, but it has to wait for 1 hour before its execution of 2 seconds, right? So although this is a simple algorithm to program, this is a simple algorithm to apply, but this is one of the disadvantage of this algorithm, and we are going to program this algorithm today as well. So this is one of the algorithms. So if you see over here, there is process 1, process 2, 3 and 4 so they are in the queue and they want to run. So which one do you think will run first? Although process 3 is the shortest process. For example, this will take 10 seconds to execute, that will take 5 seconds to execute, this takes 2 seconds, and this takes 8 seconds to execute. Which do you think, according to first come first serve, will be executed first? Obviously P1 will be executed first. It doesn't matter how much is the processing time or execution time of this process. It's first in the queue, which means that it will be run first. It will run first. So the process that will run over here is process 1, right? It doesn't matter a process has a shortest process or it has highest priority, it doesn't matter, right? In first come first serve, whatever is at the head of the queue, it will run first. Then next one is shortest job first process, or shortest job first algorithm. What it does is it will serve the process that has the shortest job, right? In this case, the burst time of the CPU should be known. So let's see this. I'm going to explain this using an example. So what happens is we have 4 processes over here, P1, P2, P3 and P4, and there is a CPU burst time. Okay, what is a CPU burst time? Now for a process, whatever the process is, it needs CPU also, and it might need an IO also. For example, it needs a printer also, right? It needs a CPU also, it needs a printer also. So CPU will, the process will request operating system that it needs CPU. So maybe first lines of code is using CPU, and then maybe next line number 6 requires something to print, right? So for first 5 lines, CPU will be allocated to the process, right? First 5 lines, for the first 5 lines of the code in CPU, in process 1's or process code, CPU needs to be allocated to it. Then at line number 6, this process requires something to print. So operating system, what it will do is, operating system will take the CPU from this process, give it to somebody else, and this process will be given the printer, for example, right? Now there is some time for this process that it is executing a CPU, some time that it is using to execute some IO devices, to work on some IO devices. The time this process takes using CPU is called a CPU burst time, right? So the amount of time that this process took to use CPU is called a CPU burst time, right? And similarly, the amount of time this process took to use IO device is called a IO burst time. But we are more considerate about CPU burst time because CPU is the most required or most demanding hardware in your operating system or in your system overall, right? So when we are talking about shortest job first, we need to have the processes. Of course, we should have the information of the processes, their ID, maybe their name and so on, but we should also have the information of CPU burst time, for how much time the processes require CPU for, right? So for example, process 1 wants to use CPU for 6 milliseconds, 8 milliseconds, 7 milliseconds and 3 milliseconds, right? So this is the amount of time for which these processes require CPU to run, right? Okay, so this is the queue we have. So if you see over here, based on this table, these are the execution time, or I'll say CPU burst time to be technically correct, but some people call it execution time as well. Well, execution time is actually the CPU time plus IO burst time. So this is called the execution time. Well, for simplicity, some people say this as execution time as well, but to be technically correct, this is called a CPU burst time. So in this case, if we are given this table, which process will execute first? Obviously 3, according to this algorithm, shortest job first, the process that has the least CPU burst time will be executed first. All right, in this case process 4 has CPU burst time of 3 milliseconds, so it will run first. It will be the first in the queue. Second one will be process 1, fine, because it's after this 6 milliseconds is the least one. Then process 3, then process 2, right? Because process 2 has the largest CPU burst time. So shortest job first is a simple algorithm again that checks the CPU burst times, and according to that it runs the one which has the least CPU burst time, or the shortest job first, right? That's why it's called the shortest job first. Now if you see over here, we might need to, an operating system does that, it needs to make sure that the processes don't wait for very long, right? They don't wait for very long. This is what we said, right? In our first come first serve, the only problem was, the disadvantage was, it might take a lot of time to run. Some of the processes might have to wait for very long, right? So what shortest job first does is it calculates the wait time for each process also. What it does is, so this is the same table which we saw in the previous slide. Now it calculates the wait time of each process as well. So for example, first process, process 4, because it's the least one, it's the smallest one, it will run first, and it will run for how many seconds, assuming that every process, so at time interval 0, we have process 1, 2, process 4. So 1, 2 and 3 and 4, all of them are available over here, and they want to take CPU to run. First of all, CPU process 4 will run, so it will run from 0 to 3 because it has 3 milliseconds. Then process 1 will run, which will run from 3 to 6 because it has 3 to 9, because it has 6 milliseconds, then 9 to 16, 7 milliseconds, then P2 will run at the end with 8 milliseconds up to 24, right? So if you want to calculate the wait time of process 4, wait time of process 4 will be 0, right? Because it did not wait for, it arrived and then it was given CPU. So the wait time of this is 0 milliseconds. So for P4, the wait time was 0 milliseconds because it arrived, and since it had the least job, shortest job, it was given CPU straight away, so it didn't have to wait for anything, right? Its wait time is 0. Then we have process 1. Process 1 came, right? After that, process 1 came. How long process 1 had to wait? Process 1 had to wait for 3 milliseconds. Why? Because for those 3 milliseconds, process 4 was running. So CPU was not given to process 1. So it has to wait for 3 milliseconds. And this is what we did over here. So wait time was 3 milliseconds. Next is process 3. So process 3 had to wait for the time process 4 was executing plus the time process 1 was, process 4 and process 1 both were executing. So this is the wait time of process 3. So process 4 was executing for 3 seconds and process 1 was executing for 6 seconds. So wait time of process 3 will be 3 plus 6, which is 9 milliseconds, right? Similarly for P2, the wait time is 16, which is the addition or sum of all the process executions. So this is the this actually is the ideal scenario where we are not taking into account the response time, right? So we are assuming that operating system was very quick in handling all of them. So there was no, I told you over here, the latency, right? So latency is almost 0 over here. This is what we are assuming. The latency is almost 0 over here. So, and we have to calculate the average wait time. So if for average wait time, we'll add all of them, we divide them by 4 because there were 4 processes, and this is the average wait time of processes when we are using shortest job first algorithm. So sometimes when you are trying to compare different algorithms, you need to find out different things, and one of those things is to find the average wait time of that specific algorithm for all the processes. So almost, if you take the average of all of them, processes have to wait for 7 milliseconds using shortest job first in this scenario. Obviously if scenario changes, this will change, but you now know how to calculate the average wait time, right? So this is the shortest job first. Now there is another algorithm which is called a priority scheduling. Obviously the name says we will give a priority to each process, and that priority is normally in the integer format. So lowest the priority, smallest this integer number, highest the priority. So process with one priority inside the priority will have the highest priority, right? Now in these cases they can be preemptive. Obviously if a process is running and a high priority process comes, then the CPU will be preempted, it will be given to something else. And non-preemptive will be in some cases the priority is given, and before actually starting the queue is decided based on their priority. So once the priority has been assigned, once the queue has been made, I'll show you the queue in a while, then unless and until the process has completed its execution, that CPU is not preempted, right? The problem what happens over here is, if there is there are 10 processes for example, and process number 9 has 10, the least priority, then it will keep on waiting. It will keep on waiting because it has the lowest priority. And this queue is normally not static, it's a dynamic queue, so new processes with high priority will keep on coming, which means that if this guy has a lowest priority, then it will just keep on waiting forever, because new processes are coming with high priority and this is just waiting for its execution. It will never work. So this is one of the problem. In technical language, this is called starvation, because it's hungry to get a CPU and it's not getting the CPU, it's starving, right? So this is one of the problems in priority scheduling. But how to solve this problem? This can be solved if we say that for certain amount of time, if process P9 is not getting the CPU, then its priority will increase. So for example, if we say that this is the decision which normally the operating system programmers take. So for example, if for 1 hour process 9 is not given CPU, its priority will increase from 9 to maybe 3. I don't know, I'm just saying. So its priority will change. So this is normally called aging. If the age of this process is increasing, its priority will somehow increase at a certain amount of time, right? So in order to solve the starvation problem, we use the concept of aging, and this is the concept of aging. And this is the example of priority scheduling. So in addition to having a CPU burst time column, we also have a priority column as well for priority scheduling, where the priorities are mentioned for each one of them. So based on this table, you can see that process 2 has the highest priority because it's starting from number 1. If it's starting from 0, this will have 0 over here. But since, just to keep it simple, we start this from 1. So 1 means it has the highest priority. So process 2 will run first. Then process 5 will run. Then process 1 will run. 3 and 4. So this is how this queue will run. And you can calculate the wait time. I will leave it to you guys to calculate the wait time. Just like what we did over here, draw this timeline over here and try to mention all these processes over here and then calculate their wait time. I'll leave it to you guys since I've already done one for you. So it will be a good practice for you guys to find out the wait time using the priority scheduling for this type of processes. Next is another scheduling algorithm, which is the round robin scheduling algorithm. It's pretty famous in operating system, this round robin. What happens over here is, now as I mentioned over here, the solution to this problem is aging. But again, for aging, we need to know for how many times for how much time the process has to run, and then when to change this priority from low to high, right? So we need to know this information as well. So round robin somehow solve this problem. What it does is, it will, in fact, let me just explain it over here. So what it does is, so if we have these processes, for example, these are the processes that are running. What happens is, each of these process, they will run for certain amount of time. All right. So for example, if the CPU burst time for these processes is, let's assume this is 5, and let's keep it even number. Let's make sure this is 6. This is 8, this is 4, this is 4, and this is, let's see, 2. All right. These are the burst time for these processes, right? Now in round robin, what happens is, the operating system will decide that for how long each process will run, and that is called time quantum Q, right? Normally this value is between 10 and 100 milliseconds, but obviously it can change based on the improvement in our hardware and so on, right? So which means that operating system will make sure that each process, since we are taking this example, I'm going to make it simple, not using 10 and 100, I'm going to use 2 over here, right? So operating system will decide Q is equal to 2, which means that each process can run only for 2 milliseconds at one time, right? So let's assume that process B comes. So this is our CPU, this is our processor. So process B came over here, its burst time is 2, and operating system will run each process for 2 seconds only, right? So it will come, process B comes, it will run for 2 seconds. Let me change this just to make sure that this diagram works. Let's see, this is 2, 4, and this is 2. All right. So process B came, CPU will run this process for 2 seconds. Why? Because at the beginning we have decided that Q is equal to 2, which means that each process can maximum run for 2 milliseconds at one time, right? So it came, it ran for 2 seconds, but it has not completed its execution, right? So 2 more seconds are remaining for its execution to complete, right? Because it was 4 milliseconds and 2 were executed because 2 is the quantum and 2 are left, right? Since it has not completed its execution, it will be taken to the end of this list. Now it will be taken to the end of this list, right? Now this is what it looks like. Now our next process is F. This is our new queue, right? D, F, D, G and A, and this is their execution. So this was 6, this was 8, this was 4, this was 2, and for this 2 were remaining, right? 2 were already executed, right? So next is F, which has CPU burst of 2. So CPU will execute this for 2 seconds, it will complete its execution, and it will not go at the end because it has completed its execution. It was 4 over here, then it will go at the end again, right? So this is the round robin technique. This is how different processes arrange themselves in a queue in a round robin fashion based on the quantum we have specified, right? This is called a round robin scheduling. I hope it is clear. It's not very difficult at all. Just try to solve it. I'm going to give you another example over here. Okay, so just to keep it simple, we have only 3 processes over here, and this is the execution time of each process. So this is 24 milliseconds P1, then other 2 are 3 seconds, and we are assuming that quantum Q is equal to, if I am not wrong, 4 over here, right? Yeah, it's 4. So Q is equal to 4 maximum. So quanta is 4. So process P1 came first. So it came first. It ran for 4 seconds over here, which means that remaining for this is 20 seconds, right? Because it ran for 4 seconds. Since it ran for 4 seconds, and it can run for only 4 seconds. Why? Because quanta is 4. So what it will do is, so I will have something like this: P1 in the queue, then P2, then we have P3. So after the first round, P1 will go at the end of the queue. So this is our new queue. So next will be P2, P3, and P1 will go at the end of this queue because it has already executed once for 4 milliseconds, right? And remaining time for P1 is 20, right? So it ran for this. Then P2 came. It ran for only 3 seconds. Now 3 is less than 4, right? So it will just complete its execution, right? It will complete its execution. P2 has completed. Then next is P3. Why? Because in the queue next is P3. So next one is like this. It has executed its execution and so on. So we have P3 and P1 left because P2 has completed its execution. Then P3 will execute for 3 seconds. It will complete its execution, and then at round number 4, P1 is the only one left. So P1 will run for 4 milliseconds each. Every time it will run for 4 milliseconds, and it will complete its execution because there are no more processes, right? So this is how our round robin scheduling works with different processes. Obviously, with the increase in the processes, this will become very, very complex, right? And they will have variable CPU burst time. It's not easy because some of the processes might end up in IO. Their turn was there, but then they needed a CPU, an IO bond task, so they have to go there. So it becomes very, very complex when you have a lot of processes over there. So I hope this round robin scheduling technique is clear to you. One last thing over here in this is the context switching. So how many context switchings will happen? So let's see the first case. In the first case, the process time, this process P1, for example, it needs 10 seconds to execute, right? And the quantum is Q is 12. So maximum it can execute in this case number 1 is 12 milliseconds, right? Since the 10 is less than 12, so it will not take any switch. So no context switching will happen because this process will complete everything over here within this provided quantum, and no switching will happen. Let's assume in case number 2, what happens is our quantum has a size of 6. Obviously process time is still 10. So it will run for first 6 seconds, then there will be a context switching happening, which means that this process P1 or whatever, it will go to the end of our loop if there are other processes. If there are no other processes and this is the only process, even then there will be one context switching happening, right? One context switch happens over here because it can run for maximum 6 milliseconds in one turn. So it will run for this, and the context switch will happen, and then next 4 milliseconds will run over here. Similarly, if we have 1 quantum, then it will run for, there will be 9 context switches, because it will run for 1 milliseconds each time, and then it will have to context switch for rest of its execution, right? So this is how our round robin scheduling works in CPUs, in operating systems. It's not very difficult. In fact, most of the algorithms, I believe, they are not very tricky. They are simple as compared to the algorithms which we studied last time, like reader writer and producer consumer problems. They are much more simpler than them. If and I'm sure you might have seen these algorithms somewhere else as well before this course. So if you have not seen them, we have studied today, and I don't believe they are very difficult at all. You just go through them once or twice and you should master them. So this is how different scheduling techniques they look like in CPU. Then there are some other advanced techniques as well, which we are going to discuss now. But up till here, this is how our initial CPU scheduling algorithms look like. Alright, let's now talk about some advanced levels of scheduling algorithms. So the first one is multi-level queue scheduling. What happens in this algorithm is, in the ready queue of the processes, there are multiple queues within that ready queue. So it's split into multiple queues. So one of them is a foreground queue, and the other one is a background queue. And the process, when it goes to a queue, it will remain there permanently. And the beauty of this algorithm is we can run different scheduling algorithms within each of these queues. So foreground queue might have a round robin algorithm, a background queue can have a first come first serve algorithm. So this is how you can run multiple levels of queues within one of the scheduling algorithms, and at each level you can run multiple scheduling algorithms. So you can also set fixed priority for scheduling also. For example, within this within these queues, for example, there is one queue, q1, which is the foreground queue. So if this is q1 foreground and this is q2, let's assume this is running round robin and this one is running first come first serve. Now within these two queues, so within these two queues also you can run your priorities. So whenever operating system is looking for this scheduling algorithm, you can say that I always want to run q1 first and q2 second, or you want to give high priority to q2 and low priority to q1, and they will run according to their priorities. So you can do that. Furthermore, what you can do is you can ask operating system to run q1 for 80% of the time. I'm just giving you an example, it can be any time, and 20% of the time for q2. So you can do that as well. So in case of priorities, you can give priorities like this as well. So this is how you can have a lot of flexibility when you're using multi-level queue scheduling algorithms. All right, and this is normally the case of multi-level queue scheduling algorithm. The highest priority is for the system processes, and it does make sense that all the system processes, they should run at a highest priority to make your system remain stable, to make sure that it's up to date and everything. That's why all the processes that are in the system process queue will have the highest priority. Then the interactive processes. Obviously your graphical user interface is extremely important, so in order to keep that up and running, it had the processes that require so the GUI that if GUI requires some processes, they have to be on the high priority. So this is the second highest priority queue. Then there is some editing of these interactive processes as well. So we want to do some editing, copy pasting over here and there, and then this queue will run again at a high priority. Then there are some batch processes also, and then there's student process. Student processes means any type of other processes. It can be user processes, it can be third party application processes, and so on. So they will be at the lowest priority as far as this type of queue is concerned. Obviously within these student processes or user processes or third party processes, you can have other different levels of priorities as well. But this is the general idea of how the processes are split based on their priority in a typical modern operating system. Then we have been talking up till now about the processes, about process scheduling also. But in the last lecture we talked about threads also. In modern operating systems, the operating system is not only dealing with processes, it's dealing at a deeper level up till the thread level as well. So each process has a thread as well. So thread scheduling is also very important when it comes to modern operating systems as well. Now when your operating system offers thread scheduling, then scheduling of thread is happened instead of processes. So if your operating system is supporting thread scheduling, then process scheduling will not happen. Thread scheduling will happen, because obviously processes are divided into threads, and if one process has one thread, even then it has at least one thread, right? So the scheduling should be done at the threads level. Now many-to-many and many-to-one models are basically based on user level threads, and they also use libraries. We use this, if you remember, last time as well, and they run on LWP. LWP is lightweight processes. Now threads, sometimes in order to make them less complex, people and developer, they also call it lightweight processes also. So threads are also sometimes called lightweight processes also. And since there is going to be competition within one process based on different threads as well to get priority to run first, there is a process contention scope as well. So within a process there is going to be competition between different threads as well, and this is called process contention scope, where each different thread wants to get or acquire CPU, but they have to compete. Now how they will compete, who will win first, depends upon the algorithms. We have already talked about few of the algorithms. Now this priority, if one of them one of these algorithm is priority, and that priority can be set by the programmer. For example, I'm just giving you an example. So if in a user program or a user process, programmer gives the highest priority to connecting to the network first and then showing the GUI, then thread with the network connectivity will run first, all right, because it has the highest priority. So this is how thread scheduling works, and obviously with threads also you will have same level of multi queues, and then you will have same algorithms like what we do for processes and so on. So the same algorithm can run on threads as well. Now since up till now we are talking about single processor. Obviously in modern computing systems, in modern computers, there are more than one threads. When there are more than one processors, if there are more than one processors, then this whole process becomes very complex, because at each processor level scheduling has to be done, and at each processor levels, each process and each thread level, scheduling has to be done. So this whole system becomes very complex, right? Now there are basically two types of multiprocessing. One is called an asymmetric multiprocessing. We talked about that, and symmetric also we talked about that. So only one process in asymmetric, only one process access the data, system data. And in systematic processing, multiprocessing, obviously they are scheduled, so each process has its own scheduling, its own process, its own queue, and so on. We talked about symmetric a lot when we were discussing about processes. So this is sometimes also called SMP. If you remember, we talked about this systematic multiprocessing, and this is what modern computers are using. So SMP is what modern computers are using. And obviously they have their own complications, because at multiprocessor level you have to maintain the symmetry, right? And we talked about SMP, if you remember. I'm not going into more detail of this. So when we are talking about SMPs and we are talking about scheduling, there is a processor affinity as well, right? So processor affinity means that processor is assigned to one process, or for example we have process 1 and then we have CPU over here. Processor affinity means the process 1 is assigned CPU, right? It's assigned to CPU, and next time one obviously there might be other CPUs as well. So for example, there are 2 CPUs in your computer. Whenever process 1 comes, it is assigned to CPU 1. This means that this process is has an affiliation with this process. So every time this process comes, it is assigned to CPU 1, right? Now there are 2 different types of processor affinities over here. One is called a soft affinity and the other one is hard affinity. Soft affinity means operating system will make sure that process 1 is always assigned to CPU 1. It will make sure, it will try its best to do that. But if it is not possible, then CPU 2 can be assigned to process 1 also, right? So it will do its best to assign CPU 1, but if it's not possible, it will just assign CPU 2 to process 1. So this is called soft affinity. It will try its level best to assign this, but if it's not possible, it will just go and assign CPU 2. Hard affinity means if it has already been told that process 1 will always be given CPU 1, then whatever happens, CPU 2 is not given to process 1. Always CPU 1 is given to process 1, right? And where we use them, we normally use them in very complex situations like video editing, for example. In video editing, if you have multiple cores, what you want to do is you want to assign, for example, CPU 1 for video editing. So CPU 1 will not do anything else except video editing, right? So there are situations when you have to do this, right? So video editing is happening all the time with CPU 1, and rest of the cores or rest of the CPUs are doing something else, right? CPU 1 will not do anything except video editing, right? So this is called processor affinity, right? I hope you are clear on that. And then there are some other properties of SMP as well, and especially when it comes to scheduling these SMPs. One is load balancing. If you have multiple processors, so if you have CPU 1, then CPU 2, and so on, and CPU 1 is handling process 1, process 2, and CPU 2 is doing nothing, this is not right. Operating system has to make sure that there is a equal distribution of load between both the processors, all right? If there are more processors, obviously there has to be balance between all of them, right? So operating system will make sure that there is an even distribution of balance between both these CPUs, considering there are only two CPUs in the system. Now, in order to achieve this balance, there are two techniques. One is called a push migration and the other one is called a pull migration. Push migration means that the operating system will periodically check each processor. So it will, operating system, let's assume after every 5 seconds, operating system will come and see the load of CPU 1 also and CPU 2 also. If CPU 1 has overload, CPU 1 has, for example, two processors assigned to it, what operating system will do is it will take this process 2 and it will assign this to CPU 2, so that there is an equal balance between both the processors, right? So this is called a push migration. Now the pull migration is something very similar. It's just that in this case, when we have two CPUs, CPU 1 and CPU 2, if two processes are working on CPU, pull migration, again, operating system, what it will do is it will make sure that no process keeps on waiting. For example, CPU 1 is assigned to processor 1 and CPU 2 is waiting for quite long. What operating system will do is operating system will take CPU process 2 and give it to CPU 2, because CPU 2 is completing its tasks earlier than CPU 1. So this is called a pull migration. So I hope you are clear between push and pull. These are just two load balancing techniques which we use in multiple processor scheduling. Then multi-core processors, we need this obviously in modern systems, and what this means is each CPU inside it has multiple cores. So at hardware level, different chips, we can normally call them cores, each CPU has multiple cores inside it. So at hardware level, different cores are assigned. Instead of having multiple different CPUs, in order to make CPUs faster, different cores are assigned to it. That's why you might have heard of name dual core and quad core. So each CPU inside it has multiple cores installed. That is called a multi-core processor. What is the benefit of having a multi-core processor? So if we have a single core processor and we have a thread over here, what happens is we have two types of cycles normally. So one is a compute cycle, just like CPU burst and IO burst, very similar concept, just that there is a compute cycle where the thread in this case will use CPU, and there is an M, which means that it will use IO, which in this case is always memory. Alright, it will always be memory instead of printer and so on. So if there is a single core, what happens is there is a CPU cycle, this is a timeline. So it will use a compute cycle, then it will go to memory stall because this process is doing something else. It's going to CPU, it doesn't need CPU over here, so it will go and check something from memory, then it will come back and use computer as CPU as well, and then so on. However, in multi-core processors, what we have over here is multiple threads can run. One thread will run on one core and the other one will run at one core. For example, thread 0 is right now running the compute cycle. Now, thread 1 wants to fetch something from the memory, so it has to have a memory stall cycle, right? At the same time, when it went for memory stall, thread 1 is given this cycle of computing, right? So it will compute over here. Instead of wasting this cycle, this thread is given that, and that can be achieved using multi-core processors. And we have discussed this using multiprocessors, if you remember, in when we started discussing about processing. So I hope this is clear. It's very similar to what we have done before, so I'm not going to spend too much time over here. Let's now talk about real-time CPU scheduling. Now, real-time CPU scheduling, what are real-time systems? First of all, we need to understand. Real-time systems are the system where we need to have some deadlines and we need to achieve those deadlines. One example is, for example, car manufacturing, right? It's not exactly real-time. It's we can normally call it near real-time. So what happens over there is, if you see that there is a system, and first of all, if you want to manufacture a car, there is a body of the car, then it moves to the next step where doors are installed to it, then it moves to the next step, bonnet is installed to the car, and so on. If car's body is a little bit late, 1 or 2 seconds late in reaching the next destination, doors will be installed at a wrong position, right? At the wrong orientation as well, right? So now obviously manufacturing has improved a lot. There are sensors when the car body is there or not. But just to give you an example, that in real-time system, what happens is it's very important that that deadlines are met properly, so that system can function properly. Now let's further understand this using two different types of real-time systems. So basically we have soft real-time systems and hard real-time systems. Soft real-time systems are the systems where we can afford to miss a deadline, right? Where we can afford to miss a deadline. Just to give you an example, for example, your assignments, right? It has a soft deadline. So for example, just because of some problem, some students were not able to upload on Blackboard, I asked them to submit me through the email. Or for example, the deadline was 1 week, but some student had an accident, and he or she approached me that I had this emergency and allow me to submit this after 2 days. So I can submit that. I can allow them to submit after 2 days. So this is a soft deadline, which even if not met, nothing very bad will happen, right? So this is called a soft deadline. And if a system is having a soft deadline, it's called a soft real-time system, where deadlines can be missed, but not many deadlines should miss. A lot of deadlines should not miss, right? 1 or 2 deadlines or fewer deadlines can still miss, and nothing bad will happen to the system. Then there is a system called a hard real-time system. Over here, the deadlines are very hard. Deadlines are hard. For example, let me give you an example of a pacemaker which is placed in the heart, for example. So it runs on a specific periodic time. It runs on specific periods, and it has a certain skip rate. It has a certain skip rate for your heart. If it skips 1 or 2 heartbeats, a person can die, right? A person can die. So it can be disastrous if it doesn't meet the deadline. If the periodic setting of that device, pacemaker, is not done properly, then heart will stop functioning, right? And it can be a disaster if the deadline is missed, right? So these type of systems are called hard real-time system. Similarly, I mean, nuclear systems are also hard real-time systems. Similarly, our plane systems are hard real-time systems. If deadlines are missed for one of the planes, there might be a crash of different planes, right? Different planes might approach the airport at the same time, or the runway at the same time, and they might crash, right? So there are some hard real-time systems and there are some soft real-time systems, and this is what is the difference between these systems. And obviously there are two important things when it comes to the system: interrupt latency. So if we come back to our operating system, interrupt latency means whenever we are, for example, if operating system has given CPU to one of the processes, and process now wants to do a print, then it will move from CPU to IO device, and the time it has taken from moving from CPU to IO device is called an interrupt latency, right? It's an interrupt that has happened, IO interrupt in this case, that has happened, which is delaying the process, right? And then there is a dispatch latency. We discussed about that also in previous slides. That dispatch latency is when process is running on a CPU and a high priority process comes, and CPU is taken from low priority process to and given to the high priority process. In the meantime, the time taken to shift your processor from one process to another process has some delays, and this is called a dispatch latency. We have discussed this already, all right? I'm not going to go into the detail. This is what I have already said, and this is just a picture for what I have already said. But I will. It's too much detail which I have already talked about, right? So let's talk about some algorithms for real-time CPU scheduling. We have talked about non-real-time CPU scheduling algorithms before. Now let's talk about some real-time CPU scheduling algorithm. So first of them is a priority based scheduling. What happens over here is exactly similar thing. A priority is given to something, and that priority should be respected by the operating system, right? In these types of systems, only soft real-time deadlines are normally used. For hard real-time systems, the deadlines should be met. It's very important that deadlines are met. For example, going back to the plane example, if a plane is wants to land and it's number 3 in the queue, but somehow plane has an emergency and it has to land first, then the priority to the high priority will be given to this plane to land, and other planes will be given low priority, so the priorities can be changed. Obviously this system can be used for hard deadlines, but then those systems need to meet the deadlines, right? And if you see over here, what this diagram is saying is a process will have at least these 3 things. It will have some processing time, right? How much time is required to process that? And there is deadline, what is the maximum time this process should complete its execution, and then there is a period, how much period is required where it has to complete its execution. So for example, this is the processing of the process. This is the deadline, so it has to complete its processing before its deadline reaches, and this is the maximum period that it can take, because it has to give maybe a quanta over here, because after that the processor will be given to somebody else, right? So these are the 3 things that are of high importance when it comes to priority based scheduling in real-time CPU scheduling, all right? The second algorithm is earliest deadline first scheduling algorithm. It's very important when it comes to your exams, so please understand this carefully. So again, since this is real-time CPU scheduling, it's important that we keep into mind the deadlines, and I'm going to explain this to you based on an example. So let's assume, just to keep it simple, we have only 2 processes, but obviously it can have multiple processes. So let's assume we have a process P1 and P2, and this algorithm will work in such a way, whatever process has the earliest deadline will execute first, all right? And it has some other things also we'll discuss in a while. So the main agenda of this scheduling algorithm is that the process which has the earliest deadline should execute first. So let's assume we have 2 processes, P1 and P2. The deadline for P1 is 50, the deadline for P2 is 80, maybe milliseconds. Let's assume this is the timeline, and P1 should complete at 50, P2 should complete at 80. I mean, not complete, I mean, okay, so process 1 has multiple tasks, so one of the tasks should complete at 50. One of the tasks for P2 should complete at 50. Alright, so process 1 has multiple tasks. Let's assume 2-3 tasks. First task should complete at 50. Second and first task for P2 should complete at 50. Every task should complete within 50 milliseconds for P1, and every task for P2 should complete in 80 milliseconds for P2 as well. Alright, and T1 and T2, these are the processing times for how long this process is going to run within this deadline. All right, this is the processing time. So T1 T1 is the processing time for P1. So process P1 will run for 25 milliseconds within this 50 milliseconds. Alright, and P2 is going to run for 35 milliseconds within 80 milliseconds for first task. I will explain you over here. It might be confusing, but let me clear it up. Okay, so we said that there are two processes, P1 and P2. So we assume that both of them are starting at 0. So P1 approached and P2 approached, and operating system has to decide how to run these processes, which process should go first. This is scheduling, right? So which process should go first and which should go after that, right? Now we said that and these are the deadlines. These are the deadlines. P1 should complete at 50, P2 should complete at 80, and next task of P1 should complete at 100. Why? Because it's 50. So 50 and 50 is 100. So there are multiple tasks for P1 and P2. First task of P1 should complete at 50. Second task of P1 should complete at 100. 50 plus 50, 100. Third task of P1 should complete at 150, right? 50 and 50 and 50, right? Similarly, P2, it has deadline of 80. First task of P2 should complete at 80. Second task of P2 should complete at 160. And similarly, third task should complete at 240, right? This is how it works. So within this first task, P1 should execute only once. This is how this algorithm works. So the first task is from 0. First task is 50, right? The deadline for completing the first task for P1 is 50. The deadline for completing the second task for P1 is 100, and third is 150. Now within this time slot of 0 to 50, P1 can execute only once. Alright, and that too for only 25 milliseconds. 25 milliseconds. Let's see to P2. P2 has a deadline for completing its first task at 80 milliseconds. P2 has the second deadline for completing its second deadline at 160. 80 and 80 is 160, right? Now in the first timeline, let me draw it here. For P2, the first timeline, so this one was for P1. So for P2, in its first task, it should complete its first task by 80, right? 80, deadline is 80. And within this 0 to 80, P2 can run only once, and that too for 35 seconds. This is what this thing means. Once again, so for P2, let's talk about P2. So P2 needs to complete its first task before 80 milliseconds, and within 0 to 80 milliseconds, this process P2 can run only once for 35 milliseconds. And similarly for P1. Let's run this and you will see what happens. Okay, so both processes, they approached over here, P1 and P2, and operating system has to decide which process should go first. Now at 0, operating system will take into consideration the deadline for both of them. So P1 has a deadline of 50, P2 has a deadline of 80. At this stage, whose deadline is earliest? Whose deadline is coming first? Obviously P1, right? 50 is less than 80, right? So operating system will say, okay, P1 has the shortest deadline or earliest deadline. Let's run P1 first. So it will run P1 first. So this is P1 which is running, and it will run for 25 milliseconds only, right? So it will run and complete its first 25 milliseconds over here, right? Because within this time slot, it has to run only once, and that too for 25 milliseconds. This is what we have done. So we have run here P1 for 25 milliseconds. So this is 25 milliseconds, and after that CPU becomes idle, right? Because CPU has only two processes to run. So why to keep CPU idle? We run, operating system decided, okay, P1 has completed, it cannot run, P1 cannot run until 51 now, until 51, right? Because we said that from 0 to 50, P1 can run only once, and it has already run. It cannot run again. It can run after 50 now, right? So this time between 25 to 50 will go wasted. What operating system will do now is, operating system will take P2, because it knows that P2 was also ready and asking for CPU. It will run P2. it will run P2 up till 50, right? It will run P2 up till 50. Why up till 50? Because the deadline of P1 was up till 50, right? It has to see whether P1 can run again or not, right? So it will see the earliest deadline, which was 50. So it will come and stop here and see. It will not stop, I mean it will check again. At 50 it will check again, all right? It will check again. Now at 50 P1 has the deadline 100, right? 100, 50 plus 50, 100. Next deadline of P1 is what? 100. We know this, right? It's 100. And at 50, what is the deadline of P2? P2 has not reached its first deadline even. So what was the first deadline of P2? 80. So this is P2. At this stage, P2 has deadline of 80, right? And P1 has deadline of 100. Whose deadline is early? Obviously P2, which is 80. 80 is less than 100. So it will run P2 for next some time as well, right? Next some time as well. Now it has run for how long? So from 25 to 60 it ran. So basically P2 ran for 35, right? For his whole 35 here, because at 50 we checked that okay, deadline of this is 80, deadline of P1 is 100. So let's run the remaining part of P2 as well. So P2 ran for 25 here. So this was 25. 10 was remaining because total it can run before 80 is 35. So this 10 will also now execute. At this stage now, at this stage P2 has completed. P2 has completed, P1 has completed, right? The first stage. Now at 60 again, we will check whose deadline is first. Now the P1's deadline is 100. What is the next deadline for P2? It's 160, right? 160 is the next deadline of P2. Whose deadline is earlier? Obviously P1's deadline is earlier. So P1 will run now. So P1 will run over here. How much time P1 can run? P1 can run for only 25 milliseconds. So it will run from 60 to 85, 20 which is 25 milliseconds. It will run for 25 milliseconds here, and it will complete its burst here, first burst here, second burst here. At this stage, at 85, operating system will see, and operating system will say, alright, what we have now is we have P1 completed, and P1 cannot run again until 100. Why? Because it has completed its 25 milliseconds, which is the only time it can run within before its next deadline, right? So it has completed. Now from 85 to 100, CPU is all idle. So operating system will say, since P2 is idle, P2 is available now, let's run P2 for some time now. It will run P2, alright? So it will run P2, and at 100, which was the deadline of P1, it will check again. So it's P1 again here, and it's P2 again. Operating system will check now. What is the deadline of P1? P1's next deadline is 150. What is P2? P2's next deadline is 160, which is lesser. 150, P1 is lesser. So it will stop P2 now, and it will start running P1 again. This is very, very important over here, right? It has never happened before in this timeline that we have preempted a process and given the CPU to another process. So over here at the deadline of P1, we checked again which process has the earliest deadline. So 150 is for P1, 160 is for P2, 150 is less than 160, which means that process 1 should complete its execution first because it has the earliest deadline. So over here we have taken the CPU from P2 and given the CPU to P1. P1 will run for 25 milliseconds, and then rest of the time P2 will run, and this process will continue unless and until one of them or both of them have completed their execution. They have all their tasks completed, right? So this is what is earliest deadline first, and this is how it works, right? I hope you guys understand. I would highly suggest you guys to try to run this on different examples. So maybe try P1 and P2 with different values, then try with P1, P2 and P3. This is quite important for your exams, so make sure you understand this carefully. Try to do some exercise for this. If you don't understand, obviously just get back to me and we can arrange a session and I can explain it to you again, but hopefully it is quite clear to you now. So this is how we work for CPU scheduling, and we have discussed several algorithms today. We have discussed several concepts. I hope these algorithms are not that difficult, so try to go through them. If you find any difficulty, obviously you can get back to me and we can arrange a session, and I can, or maybe if you want to learn through email, I can drop you an email as well. So if you have any questions, just drop me an email or meet me in my office, virtual office hours, and we can discuss further. What we're gonna do now is we're gonna do an exercise, and this is the exercise we're gonna do. I'm gonna record another video for exercise as always. So I'm gonna stop this video over here and I'm gonna see you in the other video. See you guys. Have a nice day.